Let's talk about hypothesis testing. Whenever we conduct a statistical study, usually we're interested in drawing conclusions about some characteristic of a population, right? And so for this part of our course, we're going to be thinking about drawing conclusions about a population mean mu. So we usually start with the population that we're interested in, right? We usually don't have the resources, the time, and other things that will allow us to collect data on the entire population. So we get a random sample, right? So we use some random sampling method, and we obtain a sample of size n. Remember, our goal is to estimate or come up with our best guess of our value of our population mean mu. Well, from our sample, we can calculate a sample mean x bar. And so, since that value x bar is a single number that is an estimate of that population parameter, we call x bar a point estimate of mu, right? So, if our sample is very representative of our population and we have some other requirements that are met, then we can go ahead and use that value of x bar to draw conclusions about that population mean mu, right? That's the statistical inference step. And the thing that allows us to do that statistical inference step is to use probability. And so that's why we took some time in our previous lectures to talk about the sampling distribution of X bar because it has both mu and possible values of X bar within it. So let's talk about a hypothesis test because it is one of our statistical inference techniques that we'll be using over and over again in this course. So first, a hypothesis, you can think of that as an educated guess, but is an idea, claim, or proposition that can be tested by either observations or experiments. One thing about a hypothesis is that it needs to be testable in order for it to be true science, right? A hypothesis test is a process that uses sample statistics to test a claim about the value of your population parameter. So the hypothesis test is a whole process that we're going to use in order to use our sample data, our sample statistic to draw conclusions about the population parameter. Now, I like to think of a hypothesis test as a proof by contradiction. Um, with proofs by contradiction, you usually assume that something is true, right? So we start with assuming something is true. After you assume something is true, then you gather evidence. And so it could be some logical statements that can follow from that. But for us, since we're in the statistical world, you gather evidence, in our case, it's going to be data that goes against that assumption that you just assumed to be true. And if you've gathered enough evidence to contradict the truth, then that means that that assumption that you made must not be true. It must be false. And then you can draw the opposite conclusion. All right. That's sort of how proofs by contradictions work. And I like to think of the process of the logic behind hypothesis tests very similarly. Now, a hypothesis test is not a proof by contradiction because proofs by contradictions follow logically. You follow from one true statement to a next true statement to the next true statement. And so it's pretty absolute, while hypothesis tests are probabilistic, right? And so we don't follow absolute truths. But the logic is very similar. There are multiple components or things that make up hypothesis tests. The first is that you have to start with a hypothesis. In fact, you're going to start with hypotheses, right? You're going to have two statistical hypotheses. You're going to collect data, and from that data, you're going to be gathering your evidence. And your evidence is going to be there's going to be some calculations based off of your evidence, your data, that are consumed in your sampling distribution and your test statistic. In addition to that, we're going to use these other two components, which are your p values and your significance levels. And then, based off of those four things, those four features, we'll be able to draw conclusions about what we expect our value of our population parameter to be, or what we conclude about potential values of our population parameters. Now, the specifics of each of these components is going to depend on the type of research question and the type of data you have. But pretty much almost every hypothesis test has these four things: the statistical hypotheses, a test statistic, which is related to your sampling distribution, and you have a p value, and you're going to compare that to your significance level. All right. Now, we're going to start with the case, which is one of the simplest types of hypothesis tests that you can conduct, which is a one sample t-test. So, this is our first hypothesis test. It is a hypothesis test that is used for testing claims about a single population mean. That means we're going to have one population, and if we have one population, we're going to take a random sample from that single population. So, we have one sample. And each of those individuals are measured on a quantitative variable, because our quantitative variable can be summarized using the mean. And that's what we're interested in here, is the population mean. And then last but not least, X bar is used as our point estimate for mu. We're going to get through, I'm going to go over the specifics of hypothesis tests and some of the conceptual background with hypothesis test, while at the same time explaining some features of the one sample t-test. And so we'll take some time to conceptually understand what's going on here. All right. So I said that there are two statistical hypotheses. One of them is known as the null hypothesis. Its notation is a capital H with a subscript of 0. That's the H naught, or the null hypothesis. And then we have our alternative hypothesis, which we're going to use the notation of a capital H with a subscript A. So we have the null hypothesis and the alternative hypothesis. The null hypothesis is generally the hypothesis we assume to be true and we want to gather evidence against. So we assume that this is true and we gather evidence against it. It usually represents the status quo, or that there is no effect if we're doing an experiment. For our one sample t-test, our null hypothesis, since we're talking about our population mean, is that our population mean equals a specific value. Now, I have mu equals mu naught here. This mu naught is going to be some value that we hypothesize related to what we hypothesize our population mean to be. All right. One of the things about how we're going to be writing our null and our alternative hypotheses, I will let you know that there are different conventions of doing this. We're going to use this convention here. It's probably the most recent and the most common, is to usually have our null hypothesis contain equality. All right. So for us, our null hypothesis is going to be mu equals some value. Our alternative hypothesis is H with a subscript A once again. It is generally the hypothesis that we're interested in. Usually, we're not interested in the mean equaling a specific value. We're usually interested in that mean being greater than some value or less than some value, or something of that nature. And that is what our alternative hypothesis kind of captures. Because it's usually the hypothesis we're interested in, you may see individuals refer to your alternative hypothesis as a research hypothesis or an experimental hypothesis. We're going to use the term alternative hypothesis. Now, I was just saying that your alternative hypothesis is usually that your population mean may be greater than some value, or it may be less than some value, or what have you, right? And it's going to depend on what you're interested in. And so we can kind of come up with our alternative hypothesis. Well, I'll introduce two terms here. One is known as a non-directional alternative hypothesis, and the other is known as a directional alternative hypothesis. If I am interested in testing whether my mean is greater than some value, or if my mean is less than some value, then I have a directional alternative hypothesis. So it's H sub A is that mu is greater than some value, or here my alternative is that mu is less than some value. These are directional alternative hypotheses. A non-directional alternative hypothesis is that mu does not equal a specific value. Now, when you're doing a study, you're going to choose one of these as your alternate hypothesis, right? You can either have a directional one or a non-directional, and with the directional, you will choose. But every research question is going to have one alternative hypothesis. So one null and one alternative. You get to choose based off of what you hypothesize, what the literature has said, which one you're going to use in your study. All right. All right. So we start with the null hypothesis. Then we go out and we collect our data, right? We get our sample. We calculate our sample mean, X bar, right? So our gathered evidence, when we're trying to do this sort of proof by contradiction here, is to get our sample mean X bar. That's our point estimate for mu, and that is the thing that we're going to use to draw conclusions about what we think that population parameter value would be, right? Well, to determine if we've gathered enough evidence, we need to calculate the probability of obtaining our observed X bar, so the one that we just got from our sample, or an X bar that is more extreme relative to how our alternative hypothesis is written. All right. So we're going to use our sampling distribution of X bar. Remember, I said that we assume our null hypothesis is true. Well, under the null hypothesis, we assume that our mean equals a certain value. And so if I wanted to use my sampling distribution of X bar to get this probability here, then I know that my X bar, my sampling distribution of X bar, has a mean of mu and a standard deviation of sigma over the square root of n. And that allows me to come up with a way to calculate probabilities of different values of X bar, right? And so that is why we're using this sampling distribution stuff, because it has X bar in the middle of that distribution, and then we can calculate probabilities about X bar by looking at the areas under the curve, right? And so if I were going to calculate probabilities about X bar, then one of the things that I can do is I can convert that X bar to a Z-score, and it'll change my sampling distribution to now being a standard normal distribution, right? Remember, our formula for our Z-scores is we take the observation, we subtract the mean from it, and then we divide that difference by our standard deviation. Well, our observation is our sample statistic, our X bar. Our mean is our population mean, which we have a hypothesized value for. And our standard deviation of our sampling distribution, if I go back to that last slide, is our standard error. Remember, that's sigma over the square root of n, right? And so if I go back here, my Z is nothing more than that expression there. X bar minus mu divided by sigma over the square root of n. And so if I'm going to calculate the probability of seeing my sample statistic or one that is greater in the direction of my alternative, I can convert it to a Z-score and find that Z-score and get the area under the curve, right? So that's how we're going to, that's the next step in our hypothesis test. Well, I have an issue. We know that we've converted this Z using this formula here, right? And we know we want to calculate probabilities now from the standard normal distribution. My issue here is that we can't perform this calculation if we were doing this in real life. There's no way possible to do that. And I want you to think about why. I wrote my null hypothesis here, which is what we're assuming, right? We're assuming that we know that mu equals a certain value. We've collected data from our sample, so we have X bar in this formula. So we have X bar. We assume the value of mu, and n is our sample size. The reason why we can't perform this in practice is because we don't know sigma. And it's usually the case if you don't know the value of your population mean, you probably definitely don't know the value of your population standard deviation, right? So in practice, well, in reality, we don't know mu or sigma, but because we are assuming the value of mu in our null hypothesis, it's okay, right? Mu is not a problem here. The big problem with this whole process of gathering data and then determining if I've gathered enough evidence by using the probabilities from that standard normal distribution, the real problem is that sigma is unknown. And so we have a formula with something that we can't truly calculate. But there's a way to resolve that issue. And the way we're going to resolve that issue is that we're going to use the sample standard deviation in the place of sigma in that formula for z. So this formula is going to be replacing this sigma here with our sample standard deviation, which we've been using as a capital S and a capital D as the notation. Now, this causes issues, right? Because if we're using the sample standard deviation instead of the population standard deviation, we're introducing error in that actual value of that z there, all right? And that error or that additional variability in our sampling distribution, that is not good for us. And so this says using SD in the place of sigma introduces additional variability. All right, we may be off, right? There may be some error there in our sampling distribution, which makes the distribution not necessarily normal anymore. So whereas we were focused on the sampling distribution of x bar being normal, when we replace that sigma in that formula for our standard error with SD, we are no longer necessarily in a normal distribution. So let's talk about the type of distribution that we're going to have to kind of switch gears toward. The type of distribution is known as student's t distribution, or some people call it the student t distribution. I'm probably just going to say the t distribution as an abbreviated term here. We use student's t distribution to account for that extra variability in using the sample standard deviation instead of using the population standard deviation. So it says now our standard error is SD divided by the square root of n, and we can calculate that from sample data. And so now we can truly use all of our sample information in order to draw conclusions about that hypothesis, about that population parameter in our hypothesis test. The name student in this student's t distribution or the t distribution, the statistician who created this uses a fake name, a pseudonym of student. And so that's why it's called student's t distribution. All right, a little bit of information about student's t distribution. It is a symmetric, unimodal, and bell-shaped distribution. So it's going to look very similar to a normal distribution, and it kind of works in a very similar way. We calculate probabilities by looking at areas under the curve. But remember when we were dealing with the normal distribution, we said that every normal distribution can be kind of identified or specified by knowing the mean and the standard deviation. Well, students' t distribution or t distributions in general, their parameter, they only have one parameter. So the normal distribution had two parameters, the mean and the standard deviation. But the t distribution only has one parameter. And that parameter is called your degrees of freedom. Degrees of freedom. Sometimes we abbreviate it with DF. The degrees of freedom actually has a formula. It's n, which is your sample size, minus 1. All right? So if I know the degrees of freedom or the sample size minus 1, I know the specific t distribution to calculate areas from. All right? In this graph here, I have the normal distribution, which is your solid line here. And then I have a couple of t distributions, which are your dashed curves here. As you can see, on the tail ends of the graphs, the t distributions are a little higher. So they have more area under the curve, or higher probabilities on the tail ends compared to your normal distribution. While in the middle, they are lower. That means they have less probability relative to the normal distribution. But again, it's bell-shaped, unimodal, and symmetric. One thing about the relationship between the class of t distributions and a normal distribution or a standard normal distribution is that as your degrees of freedom increases, which means as your sample size gets larger and larger and larger, the t distribution approaches the normal distribution. All right. So if I did for you math folks, the limit as n goes to infinity, it doesn't even have to be that big. It doesn't. After you get to about 30 or 40 or 50, you know, after a certain number of decimal places, the normal distribution and the t distribution are going to give you basically the same values in terms of finding areas under the curve. All right. But this is the distribution that we're going to actually calculate areas under the curve for in order to get probabilities. And so when we were originally looking at calculating areas using this z and this formula here, which is our z-scores, we're going to have a very similar formula, but now this formula is based off of the t distribution. And so this formula, I have t, this subscript s I'm going to come back to. It is the same formula that we have corresponding to z, except for we're changing or replacing our population standard deviation with our sample standard deviation here. And remember, it has a degrees of freedom equal to n minus 1. So this is the value that we need to find on the t distribution curve in order to help us calculate those probabilities. This t, this specific value of t, this is called our test statistic. All right. So t with that subscript s is known as our test statistic, and it will be used to calculate probabilities from the t distribution based off of our alternative hypothesis. Let's see how we can get there. Well, remember, depending on what our alternative hypothesis is, we're going to have to kind of think about this slightly different, or think about the actual probability calculation slightly different. If we have a directional alternative, so our research question is that, we expect the mean to be greater than some value here. Then I'm in this first scenario here in this first box to the left. An alternative mu is greater than mu sub 0. Then what I need to do when I want to find the probability of obtaining my sample statistic, our x bar, or one that is more extreme in the direction of the alternative, I'll go to the t distribution, find the point on my horizontal axis where that test statistic is, and my probability is going to be the area under the curve for any test statistic of that value or greater. So look at this graph here. My test statistic, I just chose a random one here. And since my alternative says mu is greater than 0, I need to find the area under the curve for any test statistic or that is that value are greater, and values that are greater to the right or to the right. And so a lot of times we'll call this probability and this test a right-tailed test, all right? Because the probability that's going to give us our next component is on the right tail of that t distribution. The other directional alternative, let's say our alternative was that mu is less than a value mu sub 0, then I'm going to find on my t distribution my test statistic, plot it on that horizontal axis, and since this says less, I want to find the probability of this test statistic or all of the other test statistics that are less than that. And so if I go to my t distribution, it's going to be the left tail of that graph that's going to give me my probability. And so a lot of people call this a left-tailed test. Okay? Now, when I have a non-directional alternative, We're just interested in our population mean not equaling a certain value. And so when I get my test statistic, I'm not just going to look at one side of that distribution. I'm going to have to look at both sides or both tails of that distribution. So I'm going to find my test statistic and I'm going to get all of the values that are greater than that test statistic on one tail. And then I'm going to find the opposite of that or the negative of that test statistic. And I'm going to get all the values that are less than that. And then my probability is going to be the sum of those areas on both tails of that distribution. And so the probability is the sum. And since we're using both tails of that distribution, it's called a two-tailed test. So if I have a non-directional alternative, I have a two-tailed test. And if I have a directional alternative, I have a one-tailed test, right? It's either going to be left or right-tailed. All right. So we know how to get the probability. So these are the probabilities of getting your sample statistic or another sample statistic that's more extreme in the direction of your alternative. And so the direction of your alternative should match the greater than or the less than. And then the not equal to indicates both sides. All right. The actual probabilities that we find in either of those cases there, that is known as a p-value, right? So the p-value is the probability of obtaining your sample statistic or one that is more extreme in the direction of the alternative hypothesis. That is what a p-value is. Now, if that p-value is very small, very, very, very small, so the probability of getting that test statistic or one more extreme, given that you've already assumed that that null hypothesis is true, then that's a lot of evidence against the null hypothesis, right? Because remember, we assumed that the null hypothesis is true. We collected our data, calculated our sample mean, converted it into a t, and we used the t distribution to give us a probability. If that probability is very, very small, that means that it's very, very unlikely that that initial assumption is true. And so we have that contradiction there. So if that p-value is very small, then we have gathered enough evidence to reject the null hypothesis and to conclude that the alternative hypothesis is true. If that value, that p-value, that probability value is not very small, then that means we've not gathered enough evidence. All right. And in that case, we usually say we fail to reject the null hypothesis. Now, there are some statisticians that argue that we can say, oh, well, if we fail to reject the null or we don't gather enough evidence, that's evidence, to support the actual null hypothesis. And other statisticians say this: just because we haven't gathered enough evidence in our study doesn't mean that the evidence is non-existent. We just haven't gathered enough evidence in our study, right? And so some folk don't recommend that you say we accept the null hypothesis. Instead of saying accept, we don't. Instead of saying that we accept the null hypothesis, we prefer that you say we fail to reject the null hypothesis. Honestly, as a researcher, as you get more into reading words, or not words, but literature in your field, you will see what in your specific area what they say, and you can just follow along with what they say or argue that, hey, I'm going to use the word accept and I can back up why I'm accepting this null hypothesis. As for me, I either say reject or fail to reject. I don't say reject or accept. Your textbook actually says accept the null hypothesis. I don't think that argument is big enough for us to dwell on in this course. But I will use the terms reject and then fail to reject in my examples. Now, notice in either of these cases, I use the terms very, very small or not very, very small. That is not very scientific at all, right? And so we need to know how small is small and how small is not small, right? And so this is where our significance level comes into play. Um, a significance level, which we're going to denote with the Greek letter alpha, is sort of like our standard of proof for our hypothesis test. It's a value that we use to determine what probability is small enough to say that we've gathered enough evidence, right? So that is our alpha. If our p-value is less than or equal to our significance level alpha, then we can say that we've gathered enough evidence to reject the null hypothesis. However, if our p-value is greater than alpha, then we've not gathered enough evidence to reject the null, and so we say that we fail to reject. All right, alpha is usually set prior to conducting your study, and most of the studies that are published in education, in the field of education, and social sciences in general, uses an alpha of 0.05. Do note that you can change that value, especially if your sample sizes are smaller or there's some other things that could come into play that may make a researcher change that significance level. We may talk about some of that later or throughout the semester. But generally in educational research, we use alpha equals 0.05. All right, so those are all of the components of conducting a hypothesis test. We're going to put this together now into a couple of examples so that you can see how this will play out if you're conducting a study. So in this example, it says a school implements a new reading program for a class of size 30 sixth grade students, and they hypothesize that students participating in the new reading program will score beyond the national benchmark. And by beyond, a better term will probably be above. All right. Well, the national average reading test score, and that's the benchmark here for the sixth graders, is 75. All right. So we have a sample size of 30. We hypothesize that these students who are participating in this program are going to score above that benchmark, and that benchmark value is 75. So notice here, we have one single sample. We've measured them on a quantitative variable, which is the reading test score, and we have a hypothesized value or a hypothesis that we're interested in, which is that the population mean for children in that reading program is going to be greater than 75, right? So I'm going to start by writing my null and my alternative hypothesis. I know I'm in the one sample case here, and my null hypothesis is usually something of equality, and that's going to be that my population mean reading score for children in the reading program is 75. And my alternative hypothesis is that the population mean test score for children in that reading program is going to be greater than 75. And I'm using the sample of size 36 graders and whatever their mean and stuff would be to help me do with my hypothesis test. It didn't say or give me my significance level in this example here. And so I'm going to choose my alpha to be 0.05. And our general convention is whenever we're doing a hypothesis test in class, we'll use alpha equals 0.05 if it is not given to us. I'll generally always give you an alpha equals 0.05. All right, so what we're going to do is we're going to go to JASP and we're going to import our data so that we can conduct this hypothesis test. All right, so I'm going to import my data. I'm going to go to my computer. I think, yeah, it's called the test. The data set is called week 4 test score data. I'm going to open that. This is what it looks like. Now, I did say that we're going to do a hypothesis test. Now, one of the things that is always good to do is to do some descriptives. So, for instance, we've already done or used this descriptives menu here. I'm going to have this score. That is my variable of interest. Once I select that, I can see some descriptive statistics. For instance, I know that the mean score in my sample of size 30 is 78.267 with a standard deviation of 4.193. Um, the minimum score is 71, the maximum score is 92. In addition to that, I could plot a graph to see what my scores look like visually on a, let's say, a histogram. And so this would be my histogram here. Now, I'm a little alarmed with using this mean here for the simple fact that this graph here looks a bit positively skewed, right? It looks like this tail over here is a little longer. Now, I only have 4 bins here, or well, I only have 5 intervals here for which I'm creating this histogram, but it looks a little skewed to the right. I'm going to see if that is still the case, and I also want to see what's happening over here because this may be an outlier or an extreme observation that's making my data look not normal or not bell shaped. And so I'm going to go to customizable plots here, and I'm going to plot a box plot just to see what my graph may look like. And so here is my graph. Notice here, I have a dot here, which is an indication that the maximum point is an outlier. It's much larger than the next largest or the next largest item or data value if I ordered my data from least to greatest. And then this box plot here, notice that the median is all the way over here to about, let's find the median. I'm going to add that here. Our median is 79 and our mean is a little smaller, right? Notice when we're positively skewed, our mean will be pulled towards the tail of that distribution, which would indicate that our mean would be greater than our median, which is not the case here. So although this looks positively skewed, this is probably an outlier here, and our data are probably pretty normal here. All right. Now, I'm not going to worry about this too much because I have a sample size of being at least 30, right? And while my data distribution may not be normally distributed, my sampling distribution of my sample mean, because my sample size is at least 30, the central limit theorem tells me that my sampling distribution of X bar is approximately normal, which validates or supports the fact that I can use this method to still draw conclusions. All right. So you want to look at your data to kind of get a sense of, hey, am I seeing some normality here? We're going to focus on this a little bit more as we continue more and more hypothesis tests. But always look at your sample data to get a sense of what's happening there. All right. Now, I'm going to close this descriptive menu because my goal here is to conduct. Okay, it's not closing. So I wonder why. I really want to close that. Maybe I have to open the other menu to close it. See, that one works. Ah, maybe I'll add the other menu. Sorry, it's not important here. All right, so for me to conduct the one sample t-test, I'm going to go here to t-tests. And we're going to be in the classical statistical menu, and we're going to select one sample t-test. So if I go here to one sample t-test, I'm going to select my variable. Notice here, score is here. And there are some options that I want to let you know about, right? So under the tests menu, there are 3 options here. Students t-test uses the t-distribution. Wilcoxon signed rank, that is a non-parametric test that you can conduct. And then we have a z-test. The z-test is only used when sigma is known. That's usually not going to be the case for us. This Wilcoxon signed rank, if I had enough evidence, so if I had a small sample size and my data did not look like a normal distribution, I would use this test here. Since that is not the case, I'm going to stick with students' t distribution and keep this checked. All right. Now, my null hypothesis, as we recall, was that mu equals 75, and my alternative was that mu was greater than 75. And so what I'm going to do here is I'm going to choose the greater than value under my alternative hypothesis, and then I'm going to change this test value to the hypothesized mean, right? I want it to be greater than 75, and I have that value there. All right. So to conduct the hypothesis test, I need at least these things checked here. Now notice I did use the descriptive menu up here to get all of this stuff. Let's see if it'll work now. It doesn't. That's going to drive me crazy. I'm sorry. Um, you can select this descriptives part here in this menu here, and you can get your mean, your standard deviation, your standard error, and your sample size here as well. All right. But we can see here, this is the value of our test statistic, that T with a subscript S. This is our degrees of freedom. Remember, the degrees of freedom was N minus 1. N was 30. 30 minus 1 is 29. And then here, I have my p-value under that column that's labeled P. Now, if my p-value is very small, smaller than 0.001, then it's going to give you this as your p-value. It's not going to give you the specific value. This is going to be an indication that your p-value is less than 0.001. And so from that, I can draw my conclusions based off of this hypothesis test, right? So these are the results once again. Remember that we compare our p-value to alpha. Well, our p-value is smaller than or less than 0.001, as we see here. That is less than our alpha of 0.05, which I indicated on the last slide. And since it's less than or equal to that value, we know we reject the null hypothesis. So we assumed that the population mean test score was 75. We've gathered enough evidence to reject that null hypothesis. So what we'll say is that we have sufficient evidence to conclude that the average test score for students participating in the new reading program is significantly greater than the national average. It's significantly greater than the national average. All right? That is our result. Notice here, I'm saying what my population parameter is, which is the average test score for students participating in a new program. We know that it's significantly greater than that national average. I want to be a little more careful here. I'm going to add I don't want you to think that I'm drawing conclusions about the 30 students that are in the sample, all right? So I added this term here, the population average test score for students participating in the program is significantly greater than 75. The way I had it written, it made it seem like I was talking about this class of 30 sixth grade students, and when in reality, I'm talking about the population of sixth grade students who participate in the reading program like these students participated here. All right. So I want that to be clear. Anytime we're drawing conclusions based off of a hypothesis test, we're not talking about what's happening in the sample. We already know what happened in the sample. It had a mean of 78 point something, right? Anytime we're drawing conclusions about our from our hypothesis test, it is always going to be outside of the actual participants in your study. So I added that word population there to be specific about that, okay? I'm sorry for leaving that off before. So you're drawing conclusions outside of your study, not just for the individuals in your study, but for your population of interest. All right. And so I wanted to provide an example of some conclusions or how you may want to write this up for in APA style. I think this was fine here because we're talking about the test. All right. And so in APA format, it says a one sample t test showed that the average reading test score for sixth graders participating in the program, M equals 78, standard deviation equals 4.2, was significantly higher than the national average reading score of 75. And I'm giving my test statistic, which is, I say I'm using the T. These are my degrees of freedom in parentheses. It's equal to 4.27. And then I also give my P value, which is 0.001. All right. And that gives your readers enough information to really see your results in words and not just in like charts and tables and things of that nature. All right, let's look at one additional example. It says an educational researcher conducted a survey research study on the motivation of high school students. She collected a sample of 500 ninth through 12th grade students and administered a survey measuring intrinsic and extrinsic motivation. So we have two scales here, and they both are composed of 6 Likert type items, and each of those items have 5 response categories. One of her research questions focused on the external motivation of students, where she hypothesized that the mean sum score in the population would be different from 18. Let's test this claim using a significance level of 0.05. All right. And so with this example, we're going to have our null and our alternative hypothesis. Notice here our sample size is 500. The variable of interest is the sum scores on the external or extrinsic motivation of those students. And she's hypothesized that the mean sum score will be different from 18. So remember, our null hypothesis is that our population mean would equal some value. So it's 18 here. And our alternative hypothesis would be that our population mean would not equal 18. And of course, we're using an alpha of 0.05. And so I'm going to go to JASP and I'm going to open a new data set. I think this data set is called Week 4 Simulated Survey Data. We should get a new window here. Notice here I have an ID variable. And then I have the 6 intrinsic motivation items. And then I have the 6 external or extrinsic motivation items. I have the sum of the intrinsic motivation items and the sum of the extrinsic motivation items. We're looking or worried about this sum of the EM sum, right? Just as we did before, we can calculate some descriptives. I'm going to go here. I have my EM sum. I have my mean, my standard deviation, so on and so forth. If I slide my menu over, I'm going to see my actual results. I know my sample size is 500. We have a mean X bar is 18.232, which is very close to the 18 that we are hypothesizing, which is very interesting. Our standard deviation is 4.737. I just want to take a look at a graph. Do these look normally distributed? Is it a different looking graph? So on and so forth. That's a pretty good. Sorry. It looks like it's approximately normal. So this gives me a lot of hope that, or some confidence that my data are truly from a normal distribution. With a sample size of 500, that's not completely necessary, but this is pretty good. Some pretty good evidence of normality here, and so I'm going to continue forward, even if it wasn't, because our sample size is greater than 30, we know we can still use this method because the normality assumption still holds. And so let's try this again. Still doesn't work for me. All right, I'm going to do the one sample t-test. One sample t-test. Click that there. I'm going to select my variable, which is the sum score for extrinsic motivation. I'm using our student's t-test. I want not equal to a value of 75. Not 75 was not the value, it's 18, sorry. And if I wanted some descriptives, I can get this descriptives there. But this is my test statistic, 1.095. My degrees of freedom are 499, 500 minus 1. And then this is the area under the curve under the two tail ends of the distribution, where t would be 1.095 and negative 1.095, right? And so now that I have these results here, I can draw my conclusions. And so my p-value is 0.274. That is greater than my alpha of 0.05. And so since that is the case, I'm going to fail to reject. And I do want to point out something here. This should just be a greater than and not a greater than or equal to. So since it's greater than alpha, we fail to reject. There is not sufficient evidence to conclude that the population average sum score on the external motivation scale is significantly different from 18. All right. And these are the results in an APA style format. We can say that a one sample t-test showed that the average extrinsic motivation sum score of 18.2 with a standard deviation of 4.7 was not significantly different from the population mean sum score of 18. And there's my t-test results there. All right. And so basically we start with our hypotheses, collect our data, calculate our sample mean, look at our sample statistics, our descriptive statistics to see what's going on in our sample. And if we want to extend beyond what we see in our sample to draw conclusions about our population, we get our test statistic, get the area under the t distribution curve on either the right or the left tail, or if we have a non-directional alternative, on both tails of the distribution to get our p-value. And if our p-value is less than or equal to our alpha, we're going to reject. So that equal goes with the less than. It's less than or equal to. And if our p-value is greater than alpha, then we've not gathered enough evidence and we would fail to reject our null hypothesis. All right. That is the end of this video. I'll see you in our next one where we talk about types of errors.